So my name is Mori, and now today we want to solve some problems in operating system CPU scheduling part and talking about the shortest remaining time, or SRT. Okay, let's talk about some example about one of the CPU scheduler algorithm that called shortest remaining time, or we call it shortest job next, preemptive one. So as you can see here, we have four process. So we have four process here, uh, P1, P2, P3, and P4. The arrival time for them is included, also burst time and priority. Here, most of the time we don't need the priority, but sometimes we need it. But here in shortest remaining time, we assign and allocate the CPU to the process with shortest remaining time. Okay, let's go ahead and talk about this. So for the first one, as you can see, in time zero, arrival time zero, there is only one process. So of course, the CPU is allocated to P1 between 0 to 1. But in time 1, the new process will come in the ready queue. As you can see now, after 1 nanosecond, P1 needed one more burst time, but P2 needed 4 burst time. So as you can see, 1 is less than 4, so we didn't deallocate the CPU from P1, and P1 is still continue to running until time 2. So after 2 nanoseconds, P1 completed the work and finished. So now we have P2, and on time 2, another process, P3, is came into the ready queue. So in time 2, we have P2 and P3, but the burst time for P3 is less than 3 is less than 4. So we allocate the CPU to the P3 between 2 to 3. Why we didn't allocate it until 5 because it needed 3? Because in time 3 we have a new process arrived. So P4 is came in time 3. So in time 3, P3 completed 1 nanosecond of its work. So now need 2 more. But in time 3, we have a process 4 only needed 1 nanosecond. So we deallocate the CPU from P3 and allocate it to P4. So P4 got the CPU between 3 and 4, and also this one is completed. So now we have 2 more processes not completed in the ready queue. P3, after taking 1 CPU time, 1 nanosecond CPU time, need 2 more, and P2 need 4 nanoseconds. So we allocate the CPU first to the P3 again, and between 4 to 6 it got the CPU, and then after that we allocate it to P2 between 6 to 10. So this is the Gantt chart for SRT algorithm for these processes. So let's go and start to calculating the turnaround time and waiting time as the two most important criteria in CPU scheduling. So first of all, for turnaround time means the time between the duration between completion of the process to arrival time. So now P1 is completed on 2 but arrived in 0. So we need to 2 minus 0. For P2 is completed at 10 but arrived at 1. So 10 minus 9 is for turnaround time for P2. And for P3, it's completed on 6 and arrived by 2. So 6 minus 2 for P3. And also for P4, it's completed at 4 and arrived at 3. So 4 minus 3 is for P4. So we have 2 minus 0, 2, 10 minus 1, 9, 6 minus 2, 4, and 4 minus 3, 1. So 2 plus 9 plus 4 plus 1 is 16. But we have 4 processes, so average turnaround time 16 divided by 4, and the result is 4. So another criteria is waiting time. So for waiting time, we just simply decrease the burst time from the turnaround time for each process. What it means, for process 1, the turnaround time is 2. So we write 2 minus the burst time for P1 is 2. So 2 minus 2 is the waiting time for process 1. The next one, the turnaround time for P2 is 9 and the burst time is 4. So 9 minus 4 would be 5. The next one, turnaround time for P3 is 4 and minus the burst time 3. So it could be 4 waiting time for process 3. And the next one, the latest one, we have turnaround time 1 and also burst time 1, 1 minus 1. So we can calculate it. So 2 minus 2, 0. No, 9 minus 4, 5. 4 minus 3, 1. 1 minus 1, 0. So we have 6 divided by 4 for the average waiting time, and we got 1.5. So waiting time could make sense here. Why? It means that process 1 is the arrival time is 0, and at 0 allocated CPU to it, and it's completed in 2, and the burst time also is 2. So between 0 to 2 it's not waiting for anything for getting the CPU here. Also for P3, as you can see here, P3. So P3 came on 2. So exactly on 2, it got the CPU and it completed until on 6. So it needed 3, but in 3, between 3 to 4, the allocated CPU from P3 and it's going to waiting. So here it's got the CPU by the P4. So it means that between 2 arrival time until completion time, the P3 are 1 nanosecond in the waiting for getting the CPU. Okay, so it's totally got sense. Okay, so it's for this example is completed. Let's go to the next example about the SRT. Okay, let's talk about another example for SRT. So now we have, as you see here, we have 5 processes between P1 to P5. And arrival time for 3 of them are 0, the P4 is 2, and for P5 is 4. So first of all, in time 0, as you can see here, we have 3 processes. So for 6, 5, with 6, 5, and 7 burst time, not even what priority they have, between them we choose the shortest one. So between them the shortest one is 5. So we allocate the CPU to the P2 because the burst time is less than 2 more. So we allocate CPU between 0 to 2. Why? Because until 2 there is no other process came. So it means that on process and in time 2, you can see we have another process came in the ready queue. We called it P4 here. So as you can see, 2 nanosecond here, CPU allocated to P2, and now we have, as you can see, 5 minus, we have 3 more. So we need 3 more CPU time or burst time for P2, and also we need 3 CPU time burst time for P2. So here, when they have the same, uh, burst time, so we need to get allocate the CPU with to the process with the more highest priority. So lower number means the higher priority. So P4 has priority 1 and P2 has priority 2. So it means that the priority of process 4 is more than 2. So we deallocated the CPU from P2 and allocated it to P4. So just mention that if there is the same burst time and the priority also same, so no need to get back the CPU from the current process, and current process continue to run it. But here, as the priority of the uh, you can see here the priority of the P4 is 1. It means that highest than 2. So we got back deallocate the CPU and allocated it to P4. So as you can see here, in time 4 we have another process. So in time 4, between this one, you can see here 2 nanosecond P4 is running, so I still need one more here. So I still need one more here, but P5 is coming at 4, and also this one is needed 1 nanosecond. So you can see the same here. We have the same burst time needed to needed the CPU here, P4 and P5. Also, priority are same. So when the priority are same, the current process is still continue to running. So P4 is still running until 5. So in time 5, as you can see here, in time 5, P4 is completed, and here we have 3 more, and we have P1 with 6 burst time, P3 with 7 burst time, and P5 with 1 burst time. Of course, in between them, we allocated CPU to P5 because it needed less than the others. So P5 is running between 5 to 6, and then in 6 this one also completed. So we have 3 for P2, 6 for P1, and 7 for P3. So based on because the new process is not came here, it is mentioned to came, so we have to allocate the CPU to P1 after the 3 allocated to P2 because it's less than P1, and then after it we allocate CPU to the P1, and after that also allocated the CPU to the P3 after P1 and P2 also complete. So this is the Gantt chart for this example. So let's go ahead and calculate the turnaround time and also waiting time for them. So for turnaround time, we told you the duration between process completion to process arrival. So process completion for P1, you can see is 15 minus the arrival time is 0. The next one for the P2, the completion time is 9 and the arrival time is 0. So 9 minus 0 is the turnaround time for the P2. For P3, the completion time is 22 and the arrival time is 0. So 22 minus 0 is the turnaround time for P3. For P4, the completion time is 5, arrival time is 2. So 5 minus 2 is turnaround time for P4. And for P5, the completion time is 6, arrival time is 4. So 6 minus 4 is turnaround time for them. So as you can see here, for 15 minus 0, 15, 9 minus 0, 9, 22 minus 0, 22, and this one 3, this one 2. So 15 plus 9 plus 22 plus 3 and plus 2 is 51 divided by 5 because we have 5 processes here, and the result is average turnaround time is 10.2. For the waiting time, as we told you before, the time between we have to decrease the burst time from the turnaround time for each process. So turnaround time for process 1 is 15, burst time is 6, 15 minus 6. Turnaround time for process 2 is 9 and burst time is 5, 9 minus 5. The turnaround time for process 3 is 22 and the burst time is 7. So the other also, the turnaround time for process 4 and 5 is 3 and 2. So and also the burst time is 3 and 1. So 3 minus 3 and 2 minus 1 is waiting time for P4 and P5. So as you can see here, this one is equal to 9, this one 4, this one 15, this one 0, and this one 2 minus 1, 1. So we calculate this one, and 9 plus 4, 13, plus 15, 28, and plus 1, 29. So 29 divided by 5, we got 5.8 waiting time for average waiting time for this example. Okay, let's go another example and talk about another example and have more understanding about the shortest remaining time. Okay, let's talk about the another example. Also here we have 5 processes with different arrival time and burst time and also priority. So first of all, in time 0, we have only P1, same as the other. So at the time 0, we allocate the CPU to P1 and it got the CPU between 0 to 1. In 1, we have our two processes have arrived here in time 1. One with the 8 nanosecond burst time needed, and the second one needed 7. So as you can see here, for this we got one, and we need 2 more. So as you can see here, 2 is less than 8 and 7, so P1 is continue to running until 3, and P1 is completed at 3. So in time 3, we have another process came that's called needed 5, and we have 7 and 8, also P2 and P3. So between them, of course, we allocate to the P4. So between 3 to 4, we allocate the CPU to the P4. So now at time 4, you can see here, after 1 nanosecond, we need 4 more. Okay, we need 4 more. So in time 4, we have the process P4 with 4 burst time needed, and we have P5 with 2 burst time needed. So we allocate the CPU from the P4 and allocated it to P5 here. So P5 also running between 4 to 6, and at 6, P5 also completed. So we have, you can see P1 also completed. We have 4, 7, 8. Of course, again, we allocate the CPU to P4 between 6 to 10, and it's also completed after it. And then we can allocate the CPU between to the P3 because it's needed 7 burst time and less than 8. And at the end, P2 got the CPU between 17 and 25. This is the Gantt chart for this example also. So very simple here. So as you can see, we must calculate the turnaround time. Okay, so for P1, the completion time is 3 and arrival time is 0. 3 minus 0. For P2, completion time is 25 and arrival time is 1. So 25 minus 1. For P3, completion time is 17 and arrival time is 1. So 17 minus 1. For P4, completion time is the 10 and arrival time is 0. So 10 minus 0. And for P5, the completion time is 6, arrival time is 4, 6 minus 4. So the result, waiting time, average waiting time could be 3 minus 0, 3, 25 minus 1, 24, this one 16, this one 7, and this one 2. So addition of the 3 to 27, 24, 27, this one 43, and 50, 52. 52 divided by 5, because we have 5 process, we got 10.44 average turnaround time. And also for waiting time, as you know, we must decrease the burst time from turnaround time for each process. So we have turnaround time 3, 24, 16, 7, and 2 for P1 to P5. So first one is 3 minus burst time is 3. So the 3 minus 3. 24 minus burst time 8, 16 minus burst time 7, 7 minus burst time 5, and 2 minus burst time 2. So as you can see, the result could be this one 0, this one 16, this one 9, this one 2, and this one 0. So 16 plus 9 plus 2, 27 divided by 5, and we got 5.4. Okay, This is another example about the shortest remaining time. I hope this could be useful for all of you. Okay, thank you very much for watching my video, and please support us with subscribe, like, and also comment, and also introducing this video to your friends. Thank you very much.